strict schedule, so it's a pleasure to introduce Amihay Hanany from Imperial. Who's going to tell us about tropical curves, how tropical curves appear in a natural way.
Okay, thank you very much. My talk today is actually inspired by the talk Ralph gave a few weeks ago. He took a three-dimensional knot and constructed a quiver. And from this, there was an algebra. So today, instead, what I will do is to take a tropical curve. And I will show how one can construct two quivers. Actually, it's the usual problem. You call them graphs, and not we call them quivers. But you'd so and they are. I'll just give the names. There will be the electric and magnetic. Quivers. And the idea is that once, so given such a construction, today we will focus on the construction. You could, for each one of them, study the Higgs branch. So for each, study the Higgs branch, which then leads to, so this is a well-studied point, pre-projective algebra. Or alternatively, the more challenging point, which I keep on repeating in my lecture, there's also a Coulomb branch, and it's a real challenge to try and construct some related clustered algebra object. So Coulomb branch, and here there is a question. So today, what we will do is to take a curve and see how to construct those two quivers.
Mirror in this sense? There's one graph.
Not mirror, not mirror.
So there are four spaces.
Yes, four different spaces and plenty of interesting questions one can ask for one curve, right? In fact, we will see also that curves have moduli, and as we vary moduli, we could also construct different quivers, and this will even make it more interesting. So we will see. So now the tropical curve. Let me just put the name in physics. It's called a brane web. And it has a few simple definitions. We studied this back in '97 because we were interested in understanding dynamics of branes in string theory. And later I discovered that there's a whole topic in mathematics which goes on under the name of tropical curves. And for me, it was really surprising to see that the webs that we were studying actually have their own mathematical motivation. So it's a piecewise linear curve. So here's one example, and here is another. We are going to assign, that's easy. We're going to draw them on a two-dimensional space, R2, and we're going to assign two integer numbers, which will measure the slope of this curve in R2, right? So for this, I will assign the number 1, 0. And for this, 0, 1. Okay. So in this case, I drew infinite. That's a very good question, right? So both of them, so I should think of them as infinite objects. And they can end. So here's another tropical curve. At this point, they should construct a new linear curve which satisfies the condition that the sum of those two numbers is 0, right? So if this is 0, 1, this is 1, 0, and then this will be 1, 1. Okay, so the first point is that at excellent, very good. Okay, so I'll refer you to Kirchhoff, right? So yeah, so I'll say that there is an orientation if this is PQ with a given orientation like that, then this is equivalent to the other orientation with numbers minus p and minus q. So I could think of this as minus 1, minus 1, and set orientations like this. And now the numbers do add up to 0, okay? So thank you for the question. Now, so at the intersection, I'll have intersection. In principle, I could have many lines that can meet. Each one of them would have the set of those two integers, p, pi, and qi, and I will just demand that some pi 0 and some qi 0. That's the first rule of a tropical curve, and the second is the slope of a line with numbers pq is the angle which is given by those numbers. So if we call the angle alpha, then it will be q over p, such that, so check the numbers, such that 1, 0 is horizontal and 0, 1 is vertical, and anything a PQ would have this particular slope. Okay, so that's the simplest definition of a tropical curve. And given this, we can now construct infinitely many such curves. So here's one curve like that. Okay. Yes. So then I will have sorry. So Misha is asking whether I allow the numbers p and q to have a common divisor. And so so then yes, if GCD of PQ is equal to some number k, then this is like k copies of p over k and q over k. Okay. So here's a simple example of a curve where I can put the numbers 0, 1, This is 1, 1, and this is 1, minus 1. Okay, and this is 1, 0. Okay, any questions about the construction of a tropical curve? So that's bigger. Thank you. You have to keep on reminding me this. Okay, so given such a case, let's look at the, now I'll give you an example of a curve which is interesting from the physics point of view. Okay, so here's our first example. And we can work out those integer numbers. It's quite evident from the drawing. So it's a rectangle. And we can see that this rectangle has two moduli, right? I can call them those distances, A and B. So there is a two real dimensional moduli space of such curves. More generally, if I'll have a general tropical curve, it will be interesting to count the number of moduli. All of them are real moduli, and then to study the behavior of this curve in various limiting cases of those moduli. Okay. So for this, I will construct the electric quiver. And so I'm going to take the limit where vertical lines dominate. So they put more weight on the slope. It's not part of my definition. I'll just use it in order to construct the quiver. So it's in this limit, it roughly looks like this. And now I'll construct a quiver, which is so the vertical lines now divide the vertical spaces into three regions. I have three regions, and this will give me the notion of a quiver. Here I have one segment, so I'll put a node, and there are two segments in between, and so that's a 2. To compare with another tropical curve is this. Okay, so now this would have the limit like this. And now I will have the quiver, which is 2 and 1. Okay. And again, as I said before, given a tropical curve, using this notion, I constructed the first type of quiver. Any questions? Yeah, you could also have the other thing. So I could also have like that. That's another tropical curve. And this will have the limit, which looks like this. So now I can say that's a 2, a 1, and a 1, which is equivalent to a 2 and a 2. Because I cannot make this distinction. Yes?
If I fix your rectangle and the other limit, I will get the same figure, right?
This one? Excellent. Excellent. This is a very important duality. I did not plan to talk about this one, but it's a very beautiful point, and one can write down many nice consequences of this thing. So let me give you a non-trivial example. Take this thing here. And let me put it properly here. So if I divide like that, I'll get a 3 and a 2. But if I look at it from this way, it will look like 2 and 2. Okay, so there is some nice property we could extract for those two objects. Yes?
Are the quivers you get all essentially type A with weights and vertices?
Of type A, yeah, framed type A. In principle, I could introduce periodicity on, instead of R2, replace it by T2, and then I could get something more interesting. It's might be interesting to study. I haven't put so much effort onto this. Say it again.
Why do they have the same number of parts?
Not. You mean 2 here and 2 here? You could. So you could easily convince yourself that this map from a curve to a quiver is not always possible. Whenever you'll have cases where there are no equal number of top and bottom lines, and then we'll just have to work with the curve itself and without the notion of a quiver. But that's an important question. Or alternatively, you could add extra lines which will make it equal, and then use the moduli to take limits of them. You'll say that it's a limit of a curve which we understand using quiver, but with a particular limit where you send values. So yeah, so for example, here, the number of parameters, I have 3 parameters. I have this, I have this one, and I can take this. So 3 parameters, and I could take limits. For example, I can take this one to infinity, and I will get this as a limit. Or I could do other limits, could send this one to infinity. Questions? So now I'll construct the magnetic quiver. So let's focus on the first one. And look for sub curves. A subcurve is a curve which satisfies the properties of a tropical curve. And it's made out of the objects I already have. So here, this configuration doesn't have a subcurve. It's just only the subcurve of itself. However, what I can do is to take those moduli, I can take them to 0. Now I'll get this topical curve. And clearly here, I do have two subcurves. Okay, so I can split them. And now I will use the magnetic quiver. I will assign a node to each subcurve. With label 1, or more generally, a number of copies. So it's that number K that we had over there, the GCD, right? The basic curve. So here I have one copy of the 1 minus 1 curve and one copy of the 1, 1 curve. And I'm going to define an intersection number. Between a curve PQ and another curve P prime Q prime to be PQ prime minus P prime Q and absolute values. So just put them into a determinant, 2 by 2 matrix, and take the determinant. And so in this case, you'll find that the intersection number is 2. So now I take those ingredients. I have 2 curves, so 1 node per each. There's 1 copy of each, so label 1. And the intersection number is 2, so I'll put 2 edges connecting them. If there was intersection number 1, then it would be 1 edge. So the intersection number is the multiplicity of the edge that connects them. This is now the affine A1 diagram. And the Higgs branch is C2 mod Z2, as could be quickly computed, and also the Coulomb branch. Questions? More like the Klein A1. Conifold would be, sorry. Matt was asking the question if this diagram is the diagram for the conifold. It looks similar, but it's different. Let me draw the two. So the diagram for the conifold will look like this. with the superpotential, which is quartic. And for this would be like this, with two loops, and the superpotential is cubic. And the tilings are different, right? The one is a square tiling, the other one is a hexagon tiling. More questions? Okay, so let's make the connection to toric diagrams. So there is a one-to-one correspondence between a tropical curve and a toric diagram. Take the following dual graph. Replace a face by a node, and an edge by orthogonal edge. So for this case, I will get a toric diagram, which is a single point in the center and 4 points. So I have 4 non-compact faces. So 4 points. And there are edges which corresponds to these 4. Those will be the dual to the rectangle. And there will be the external legs, which are those 4 edges of a polygon, right? So, so there is a one-to-one correspondence, a very simple thing. For this, I will have, well, let me draw bigger. Yeah, I might take, I might get the orientation in the wrong way, but that's roughly what it is. I think it's right. Just check what I did.
Depends on the triangulation as well as on how the diagram.
Very good. And this triangulation has significance, which I will not have time to talk about. It could also be subdivision, not just the triangulation, and at which point there will be vertices which are more than trivalent. It will be higher valency. So I could take, I could remove this one, and that will correspond to setting the length of this edge to be 0. Questions? So you may recognize that this topical curve corresponds to the toric diagram of Del Pezzo 3, for example, if you're familiar with this. Next, let's see interesting phenomena. So let's focus on this one. And you see again that for this, if I start with this curve, it doesn't have any subcurves. I cannot divide it into subcurves, which will satisfy the initial rules. However, I could take all of the moduli of this curve to 0. Then I will have subcurves. So let's take them to 0. It will be like this. And what I find is that there are two subdivisions. In toric geometry, this is important for understanding some deformations. But here, it's going to give me two types of quivers, right? Because one subdivision will be to have this curve, and this curve. And since I have three subcurves, I'll have three nodes, each one with label 1. And a quick computation of the intersection numbers will give me this quiver, which is affine A2. Do you see this? I see that Emily is raising the head. So, so I'll get this one. On the other hand, I have another subdivision, which is this one. And here. These are two different subdivisions. This one will give me another quiver, which now has two nodes, each one with label 1. And a quick computation of the intersection will give me what we had before, which is affine A1. I see. Thank you. How much time do I have? Alistair is standing. That's dangerous. Excellent. So let's summarize. Yes, let's summarize. So okay, as you could imagine, we could have many nice phenomena from studying these curves. Give me a very rich structure. And what we saw is that given a tropical curve, we have two types of quivers we can construct. We get two types of moduli spaces we could get out of that. And there is plenty of things we can do with the algebraic structure. Thank you. It's not equal. So the moduli space will be a union of the, yeah, so the Coulomb branch here is the minimal nilpotent orbit of SL3 closure. The Coulomb branch here is the minimal nilpotent orbit of SL2 closure. And if you're familiar with there is some generalized notation for the algebra E3. So the Peltzert 3 is associated with the algebra E3, which is A2 sum A1, which is what we got from this construction. Yeah, and we can construct very nice examples and study them. So it will be nice to give some algebraic context to all of this. Yes, there is. But to explain this would require many other concepts that I did not introduce. So yeah, there is a very deep connection, Actually, this introduction of the magnetic quivers from the physics perspective solved a problem which was standing for the order of 10, 20 years, 25. And so it's the physics context is really exciting. And these are not, this is not, it's a different phenomenon. It's a, thank you, yes. So Alistair was asking whether this is related to mirror symmetry. And the answer is no, it's a different phenomenon. For those who know, this is reflecting the physics of 5-dimensional gauge theories. And mirror symmetry has different names. It could be mirror symmetry between Calabi-Yau manifolds, which are compact and smooth. It could be 3D mirror symmetry, and this is a phenomenon in 3 dimensions. These phenomena are relevant to 5 dimensions. So very different phenomena. No, very. Yes. However, those questions are only relevant to Alistair. He's the only one. Okay. So, very good.
Okay, well, let's thank Amy again.
Thank you very much.
Can we have a almost 2.10 minute break and we start again at 2:30?